Welcome back to the Cisco Introduction to Networks lecture series. This is module 6 and we will be looking at the data link layer. If you like to look at the previous modules and go through those lectures, I will leave a link below in the description for the playlist for those items. So let's get started. The objective of this particular module is to explain how media access control in the data link layer supports communication across networks. We're going to learn about purpose of the data link layer. We're going to learn about topologies, and we will learn the data link frame. You should be able to describe the purpose and the functions of the data link layer and compare characteristics of media access control methods in WAN and WAN and LAN topologies. You should also be able to describe the characteristics and functions of the data link frame at the end of this lecture. So what is the purpose of the data link layer? If you look at the OSI model, you will have 7 layers or 7 sectors. It starts from physical, data link, network, transport, session, and go all the way up to presentation and application. We looked at the physical layer in our previous presentation. So now we're going to focus on the next layer on top of that physical layer, which is the data link. The data link layer is used for things like MAC addresses, which is the physical addressing, and it is ensure data is error free. The data link layer of the OSI model sits on the level 2 or layer 2, as I mentioned before, as shown on the figure on the right hand side. It prepares the network data for the physical network. The data link layer is responsible for the network interface card or NIC card to the network interface card communications. The data link layer does the following things as part of its functions. So remember, when you plug in your network cable to the NIC, the network interface card through RJ45, you're actually using the data link layer. And also the physical layer as well, which we discussed in the previous module. The data link layer enables upper layers to access the media. The upper layer protocol is completely unaware of the type of media that is used to forward the data. Data link layer accepts data, usually layer 3 packets such as IPv4 or IPv6 packets, and encapsulates them into layer 2 frames. Data link layer also controls how data is placed and received on the media. Data link layer also receives encapsulated data, usually layer 3 packets, and directs them to proper upper layer protocols such as network and transport and etc. etc. And data link layer also performs error detection and reject any corrupt frames. And we will learn about this as we go forward. The data link layer is responsible for network interface card to network interface card communication within the same network. So in other words, if you have a computer and you connect that computer to a router, like most of you have done in your home, that is using the network interface card to a network interface on the router or a server to connect with each other, and that is facilitated by the data link layer. It allows upper layer protocols to access the physical layer media and encapsulate layer 3 packets, which is IPv4 and IPv6 packets, into layer 2 frames. It also performs error detection, as I mentioned before, and it rejects the corrupt frames so that the data can be received from the other end with all the information that it needed to communicate. The IEEE 802 LAN /WAN data link sublayers can be summarized like this. The data link layer consists of two sublayers. They are called Logical Link Control (LLC) and Media Access Control or MAC. Most of you are probably familiar with the Media Access Control or MAC because you probably heard about the term MAC addresses, which oftentimes been thrown around, especially when you're working with networks. So in here on this diagram, you have the physical layer and then you have the data link layer. And on the data link layer, we have these two subcategories, the MAC sublayer and the LLC layer. So what is Logical Link Control or LLC? LLC handles communication between upper layers of the protocol suite and lower layers. LLC is implemented in software and its implementation is independent of the hardware. Typically, the driver software for a network interface card, like for example, if you have Intel network interface card on your computer, the driver for that network interface card should be responsible for LLC, the logical link control. It identifies which network's layer protocol is being used for the frame. This information allows multiple layers 3 protocols such as IPv4 and IPv6 to use the same network interface and media. The Media Access Control, which is the one most of you are familiar with, or MAC address or MAC control, what it does is the MAC sublayer is responsible for data encapsulation and media access control. MAC sublayer defines the media access processes performed by the hardware. It manages the frame access to the network media according to the physical signaling requirements such as copper cable, fiber optics, wireless, etc. So MAC layer sublayer is the one who is responsible for managing the signaling requirement for each one of those categories, for example. And the MAC sublayer controls the network interface card and other hardware that is responsible for sending and receiving data on the wired or wireless LAN or MAN medium. The MAC sublayer provides data encapsulation for frame delimiting. The frame delimiting process provides important delimiters to identify fields within a frame. These delimiting bits provide synchronization between the transmitting and receiving nodes. It also provides addressing. Addressing provides source and destination addressing for transporting the layer 2 frame between devices on the same shared medium. In addition to that, the MAC layer also responsible for error detection, which includes a trailer used to detect transmission errors. Packets exchanged between nodes may experience numerous data link layers and media transitions. At each hop along the path, a router performs 4 basic layer 2 functions. So each time that your packet goes through a router, whether it's your home router or your ISP router, or you have multiple routers within a building, such as at your work, when the packet passes through from your computer to through those routers, it accepts a frame from the network medium and it de-encapsulates the frame to expose the encapsulated packet. Then it re-encapsulates the packet into a new frame, and then it forwards the new frame on the medium of the next network segment. So these are the things that the basic layer 2 functions that each router performs when a packet passes through, which is part of the data link layer process. The data link layer protocols are defined by engineering organizations such as IEEE, ITU, ISO, and ANSI. For your Cisco exams, what you need to learn is that the data link layer standards are universally managed by multiple organizations. You don't need to know specific of what each organization have done for data link layer standardization, what you should know, this organization does exist and they are the one who's responsible for standardizing data link standards. Let's look at topologies. The topology of a network is the arrangement and relationship of the network devices and the interconnections between them. There are two types of topologies used in network engineering to describe networks. They are physical and logical. The physical topology shows physical connections and how devices are interconnected, while the logical topology identifies the virtual connections between devices using device interfaces and IP addressing schemes. Just reading out these slides, it probably not going to make any sense to you. So let's look at some diagrams and then try to understand how physical topology is different from logical topology. So the data link layer sees the logical topology of a network when controlling the data access to the media. It is the logical topology that influences the type of network framing and media access control use. So the physical topology doesn't really have any impact on the network data link layer. The logical topology does. So based on the definitions of the previous slide, if you just look at these two diagrams, as I mentioned, you probably have now a better grasp, better idea about how the physical topology is differ from the logical topology. So in this example, the physical topology is divided or sectored based on the room in which these devices contain. So for example, this router and these two switches and these devices, these end devices, in this case servers, are located in room number 2158. So physically, we're going to separate this into that room, as opposed to in here, in logical topology, the switch and these end device servers, in this case web server, email server, and file server, logically separated from the switch 2, because switch 1 is connected to switch 2 via a router, and then that router is responsible for logically separating the switch 1 devices from switch 2 devices. Therefore, in logical topology, we separate this as a one section, and this section is another section, and these are as three different other sections. But in physical topology, it is divided based on the room. Like for example, this switch and this router and this switch are all located in one room. So in physical topology, we categorize all of them into one room, while this printer and this computer is in another room. So we're going to put it into another category. However, in logical topology, this printer and this S2 switch are in the same logical section, because that logical section is separated by this router in the middle, this R1. Therefore, even though this switch may be in the same room as this switch, the switch number 1, they are logically separated. We will discuss how logical and physical separation work as we move through this course materials in the future. But just for now, what you need to remember is physical topology is based on the location of the device, while the logical topology is based on the separation of the network in the logical space. So that's very important. And in data link layer, use the logical topology, not the physical topology. WAN topologies. There are three common types of WAN topologies. WAN stands for wide area network. They are point-to-point, hub and spoke, and mesh. The point-to-point is the simplest and the most common WAN topology. Consists of a permanent link between two endpoints. Like you're going to have two endpoints and they're permanently connected with the one link. Hub and spoke system is similar to a star topology, where a central site interconnects branch sites through point-to-point links. You probably have heard this term hub and spoke if you ever research how airline industry works, for example. So it looks like a star topology, but basically you have a central hub, just like a airplane, main center, for example, and then everything else connected to that central hub, and then there are spokes. It's from the central hub, every other device is connected through that hub. So that's what the hub and spoke system. Then finally, the next one is the mesh. It provides high availability, but requires every end system to be connected to every other end system. So in other words, in the mesh system, each device is connected to each other's device connections. So it's going to create like a mesh. And we will look into those items in next few slides. So point-to-point WAN topology is a physical point-to-point topology that directly connects two nodes. The nodes may not share the media with each other's hosts, because all frames on the media can only travel to or from two nodes. Point-to-point WAN protocols can be very simple. So that's a very important concept, because all frames on the media can only travel to or from the two nodes. The point-to-point WAN protocols can be very simple. For example, you have a node here, so there's a router here, and you have a network, and you have a node 2, there's another router here, and they are communicating across, and it's just going to be point-to-point because they are basically connected to each other, just like a straight line, right? So that's what the point-to-point WAN topology look like. It's a very, very simple form of point-to-point. LAN topologies. End devices on LANs are typically interconnected using a star or extended star topology. Star and extended star topologies are easy to install, very scalable, and easy to troubleshoot. Scalable means basically you can add more devices as your company or organization grows. And it is easy to install because it has a central hub. You could interconnect everything through that central hub. The early Ethernet and legacy token ring technologies provide two additional topologies. Those are called bus and ring. In bus topology, all end systems chain together and terminated on each end, while ring topology, each end system is connected to its respective neighbor to form a ring. In modern day, in 2022 and so moving forward, you will hardly see any company or organization implementing bus or ring topologies, but you will find a lot of companies implementing star topology, which is the most commonly used technology nowadays. There are a lot of drawbacks associated with bus topology and ring topology, and we will not go into depth in this module on those drawbacks, and I will post a separate video discussing extensively different topologies and advantages and disadvantages of them. But for now, what you need to understand is that most commonly used topology nowadays on LAN is the star and extended star, and the bus and ring were like legacy topologies. And on your right hand side, if you look at the diagrams as the Cisco provided, it shows the star topology, what it looks like. So it has a central point and all the end devices are connected to that central point. The extended star topology will have those central points along another connection. So in this case, there's two connection end points, central points, and they are interconnected. And in the legacy topology, such as bus topology and ring port topology, bus topology is like a straight line, and then everything connected to that straight line, they are terminated on either end. And then the ring topology will have this kind of connection. So what you need to understand for your exams, if there is a question where Cisco give you these 4 diagrams and ask you to identify them, you should be able to identify them. And you should also remember bus and ring topologies are legacy topologies, and they are currently kind of not in use and maybe in experimental use in maybe laboratories. That's it. Like in real world, we probably never going to use bus and ring topologies in 2022. So you need to remember that for your exams. So know how to identify them on a diagram, and know there are 2 items here like the bus and ring, they are legacy topologies, while the star topology and extended star topology is being used even in modern day. Half and full duplex communication. Again, just want to point out, we are not going to go into depth of these these two. It will be much more advanced for this particular course series, this lecture series, but I will explain that in a different lecture series as we move forward. But for this course, only thing you need to remember is the half duplex communication only allows one device to send or receive at a time on a shared medium, while the full duplex communication allows both devices to simultaneously transmit and receive on a shared medium. And also half duplex use on WLANs, wireless LANs, and legacy bus topologies with Ethernet hubs, while the full duplex is used by Ethernet switches that operate in full duplex modes, including routers, switches, and everything else. And why we still talk about half duplex is because the WLANs, which are wireless communication systems, which use half duplex communications. So for this course, what you need to remember is half duplex, one device to send and receive at a time. Full duplex allow both devices to simultaneously transmit and receive on that shared medium. So that's what you need to remember for this course. On my wireless lectures, wireless communication lectures, I'll be posting in the future. I'll be talking a lot about how half duplex works. But for now, just remember these two definitions. Access control methods. All hosts connect to a shared medium. So that means there are multiple access. Ethernet, LANs, and WLANs or wireless networks are examples of multi-access networks. A multi-access network is a network that can have two or more end devices attempting to access the network simultaneously. Contention-based access. So in contention-based multi-access networks, all nodes are operating in half duplex, competing for the use of the medium. Remember the definition of half duplex? So that's where this is coming into play. However, only one device can send at a time because it's half duplex, and therefore there is a process if more than one device transmit at the same time. So in half duplex, only one device can communicate at a time. So now we need to make sure that's not going to impact the quality of service or how the data is transmitted. It's not going to create collisions, for example. So how it works is all nodes operating in half duplex competing for use of the medium have certain so all nodes operating in half duplex competing for use of the medium. The examples could be CSMA CD and CSMA CA. So those are carrier sense multiple access with collision detection, which use on legacy bus topology Ethernet, and the other one is the carrier sense multiple access with collision avoidance, so CSMA, which is used on wireless LANs. CSMA, the carrier sense multiple access with collision avoidance, is still being used, while the CSMA/CD version is not really used in modern day. So CSMA CA is the one that you will be focusing on in your future lectures as well. Control access. Control access is a deterministic access where each node has its own time on the medium, and it is usually used on the legacy networks such as token ring, and you don't need to learn a lot about it, you don't need to know a lot about it, but you just need to know it does exist. So there's a contention based access and control access. You need to know those two exist, but the control access is not something that we will be focusing on any of our lectures. So we can summarize the carrier sense multiple access with collision detection just like this. So all devices listen for transmission. If no transmissions, then device can transmit. If a collision is detected, which is a spike in voltage, every device backs off a random amount of time. So it's not a fixed amount of time, it's going to be a random amount of time. CSMA is rules governing how communication occur to avoid collision. So CSMA, the carrier sense multiple access with collision detection, or carrier sense multiple access, is a set of rules that actually governs how the communication occurs to avoid the collisions. So it is a standard used by 802.3 Ethernet networking technologies. While the Ethernet networks are designed with CSMA CD technology, with today's intermediate devices, full duplex connections, collisions do not occur, and the processes utilized by CSMA CD are really unnecessary. So remember that. While the Ethernet networks are designed with CSMA CD technology, with today's intermediate devices with full duplex connections, collisions rarely occurs or never occurred because they are using CSMA CD. Wireless connections, however, in LAN environments still have to take collisions into account, because remember, wireless connections are still half duplex. CSMA CD used by legacy Ethernet LANs operates in half duplex mode, where only one device sends or receives at a time, uses a collision detection process to govern when a device can send and what happens if multiple devices send at the same time. CSMA CD collision detection process involve devices transmitting simultaneously will result in a signal collision on the shared media. Devices detects the collision, devices wait again a random period of time and transmit data. So you need to know these things for your exams, but this is probably the most detail you're gonna go into in this particular course series, but you need to know this information. So make sure you know this slide for your exam, as well as the next few slides as well. CSMA-CA is used by IEEE 802.11 wireless LANs, operates in half duplex mode, where only one device sends or receives at a time, uses a collision avoidance process to govern when a device can send and what happens if multiple devices send at the same time. CSMA-CA collision avoidance process involved when transmitting devices also include the time duration needed for the transmission. Each device on the shared medium receives the time duration information and know how long the medium will be unavailable. So instead of being random, it will know that the other devices would know how long the other device need to communicate. Again, it is very important you know these items. And in this situation, CSMA-CA is being used in modern day wireless networks. Is a very important key concept that you should understand. Again, this slide is very important for your exams, and make sure you know these items and you remember those differences and similarities between them. Data link frame or data link frame. The data link protocol is responsible for network interface card to network interface card communications within the same network. Data is encapsulated by data link layer with a header and a trailer to form a frame. A data link frame has three parts: header, data, and the trailer. So the header at the top, at the front, and the data in the center, and the trailer in the back. The fields of the header and trailer varies according to data link layer protocol. The amount of control information carried within the frame varies according to the access control information and logical topology. An Ethernet frame is not processed and is discarded if it is smaller than the minimum, or if the calculated frame check sequence or the FCS value does not match the received FCS value. So that's an important concept. So Ethernet frame is not processed and is discarded if it is similar than the minimum, which is a 64 bytes, or if the calculated frame check sequence or FCS value does not match the received FCS value. That's an important concept that you should remember. Frame fields. So we have the header, we have the data, which is the packet, and we have the trailer. The header can be divided into frame start, addressing, type, and control. And then the trailer can be divided into error detection and frame stop. This is very important concept. This is a very important concept for your exams as well as your future networking careers. So make sure you understand that. So the frame start and stop identifies the beginning and the end of the frame. The addressing indicates the source and destination MAC addresses. Remember, every packet must have a source and destination information, so the addressing will be taking care of that. The type identifies the encapsulated layer 3 protocols such as IPv4 or IPv6. So the type will denote type will dictates whether it's IPv4 or IPv6. Control identifies flow control services such as QoS. So if you have a voice packet as opposed to a data packet, and if you have QoS implemented on your network, this control will be responsible for letting the system knows how the flow control should be managed. So if it is a voice packet or a video packet, it will get a higher priority over a data packet, for example. The data, which is the packet itself, contains the frame payload. That means whatever the data you are trying to send. Error detection is used for determining transmission errors. So just to prevent any transmission issues. And the stop frame, which is not on this list, is basically showing the end of that frame that you're sending. So the data link layer protocols add a trailer to the end of each frame. In a process called error detection, the trailer determines if the frame arrived without an error. It places a logical or mathematical summary of the bits that comprise the frame in the trailer. The data link layer adds error detection because the signals on the media could be subject to interference, distortion, or loss that could substantially change the bit values that those signals represent. A transmitting node creates a logical summary of the contents of the frame known as the cyclic redundancy check or CRC value. This value is placed in the frame check sequence or FCS field to represent the contents of the frame. So it's like a fingerprint. In the Ethernet trailer, the FCS provides a method for receiving node to determine whether the frame experienced transmission errors. So that's what you need to understand about the trailer does. Layer 2 addresses, also referred to as a physical address. A layer 2 address is also known as a physical address. It contained in the frame header, like it is contained within the frame header, used only for local delivery of a frame on the link. So it's basically only using the local delivery. For example, from this computer end device to this router's port, it will be using the physical addresses. And they get updated by each device that forwards the frame. For example, when this user sends a packet, the physical address of the packet from this end device, in this case the computer, to the router's port on the left hand side is the same, but when it leaves the router on the right hand side port, it will have a new physical address of that router's port until and then it reach the next router. So that's what it means by it updated by each device that forward the frame. So each time it gets forward from this node to the next node, like this router to the next router, when it gets forwarded, that physical address changes. And that's what you need to understand in this layer 2 addressing in this slide. LAN and WAN frames. The logical topology and physical media determine the data link protocol use. So this is basically a quick summary. LAN is Ethernet as well as 802.11 wireless network. Ethernet is the wired network. WAN or wide area network includes point-to-point network or PPP, high-level data link control HDLC, and frame relay. I will go into depth of high-level data link control and other concepts related to WAN as well as also LAN in a different lecture. But for now, just remember these items fall under what category. And each protocol performs media access control for specified logical topologies. So those are the key things you should get out of this lecture. We will go over a summary next. So what did we learn in this lecture? So for your quiz or your the module exams for Cisco NetAcad, what you need to remember from this lecture is the data link layer of the OSI module. It prepares network data for the physical network, and data link layer is the layer 2 of that OSI model. The data link layer is responsible for network interface card or NIC to network interface card to communications. So a NIC to NIC communication is facilitated by the data link layer. The IEEE 802 LAN MAN data link layer consists of the following two sublayers, which is the LLC and the MAC. Remember, we learned about LLC and MAC. And the two types of topologies used in the LAN and WAN networks are physical and logical. And remember how we covered the physical, how physical is different from logical, and you should be able to separate those two. Three common types of physical WAN topologies are point-to-point, hub and spoke, and mesh. You just need to know what they are. You don't need to know in depth, but you should be able to understand the basic concepts behind point-to-point, hub, and spoke, and mesh. Half duplex communications exchange data in one direction at a time. Full duplex sends and receives data simultaneously. And remember, half duplex is being used mostly on WLAN or wireless communications in modern day technologies. In contention-based multi-access networks, all nodes are operating in half duplex, such as WLAN, for example. Examples of contention-based access methods include CSMA/CD for bus topology, Ethernet LANs, and CSMA/CA for WLANs or wireless networks. While the bus topology are considered as like legacy, WLANs are not legacy. They are still in use for modern day wireless communications. The data link frame has three basic parts, which are header, data, and the trailer. The frame fields include frame starts and stop indicator flags, addressing, type, control, data, and error detection. And you should know how to describe them and the definitions of those and why they exist. Data link addresses are also known as physical addresses. Data link addresses are only used for link local delivery of frames. So data link addresses are only used for link local delivery of frames. So remember, between routers, the data link address is going to be the same, but when it goes to the next router, that hop going to change that data link address. So that's a very important concept you should understand. So this is just a summary of terms and commands that you should know. The LLC, MAC, IEEE, what they did for standardization is not that important, but what you need to remember is IEEE, ITU, ISO actually standardize, and ANSI standardize things. You need to understand the separation between, differences between physical and logical topology. You need to understand the differences of half duplex and full duplex. You need to understand the concept of CSMA-CD and CSMA-CA. And you need to understand cyclic redundancy checks, CRS, and how it, being used in packet switching. You need to understand the contention-based access and control access. So it's already discussed in my summary, but it is just to give you a quick overview. You can pause the video here if you just want to have a quick overview, for example. And that's the end of this module. And as always, please make sure to thumbs up and subscribe to my channel. And I will be posting the future lectures within next few weeks. And I hope you score high on your exams, and all the best. And if you have any questions or comments, please leave a comment below and I will try to get back to you. And until next time, have a nice day.